there's a aspect of formalism. So there are a lot of questions on formalism, like Pauli matrices and exponentiating matrices, etc. And then Hermitian conjugates. So Hermitian Pauli matrices, Hermitian matrices. How to find eigenvalues, eigenfunctions of matrices. These are all related to quantum mechanics, but they are like formalism. So we won't be covering any of those things. And when it comes to approximate methods, variational methods, variational technique, that we won't be covering. And there are also time independent problems. Time independent, WKB. And there are many other things like identical particles. This I will touch upon in atomic physics. Identical particles. What else? Scattering. So I won't be looking at this, 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 this. So these are the things I'm still not covering. There are many things because given our time, we should do completely whatever we can. So because of that, my choice of topics is bit elementary. Nevertheless, they are important. If someone wants to ask questions in quantum mechanics, it's a 70% chance that they pick the topics I discussed. And then there'll be questions on these aspects like formalism, variational methods, time independent problems, identical particle scattering. There's only 30% chance that you get problems from these areas because these are advanced topics and we expect our students to know basics. That's why I chose topics which are very important and basic. So let's continue. Let me talk about harmonic oscillator in 2 dimensions. Harmonic oscillator in 2 dimensions. Harmonic oscillator in 2 dimensions means you can think of a potential which depends on both x and y. It oscillates with frequency omega along the x direction. And it also oscillates. That means the particle is in a potential which has both x and y coordinates, but the potential depends on x square and y square. It's a 2-dimensional potential. So particle is moving in a 2-dimensional potential, which has this kind of form. So you can imagine your 1-dimensional harmonic oscillator like upwards, U-shaped one. This is 1-dimensional harmonic potential. You rotate, revolve it in the xy plane, you get this kind of a potential. So without solving, you should always remember when you have this kind of a system and its eigenvalues, energy eigenvalue. I am always talking about energy eigenvalues. Eigenvalues depend on 2 integers. We label them nx and ny. These nx or ny, for example, they go from 0, 1, 2, 3, and so on. And ny, they go from 0, 1, 2, 3, and so on. Let me write typical energy. Total energy depends on 2 quantities for each harmonic oscillator. So because x and y are not mixing, we can think of them as independent harmonic oscillators. And first one has energy this much, x oscillator with frequency omega. The second one has this much energy. So if someone gives you values of nx and ny, you will know the energy value, total energy value. And even your eigen functions depend on nx and ny. For example, I am looking at, let's say, psi1, 0. That means x oscillator in the first excited state, it has some constant. X, that means something like this. This is the x part. And y part is in the ground state. So that is minus some another constant y part, sorry, y square. So it's a product of two wave functions. This is the wave function. So this is how it looks like. Let's spend some time, because it's important, on energies. For example, nx is equal to 0, ny is equal to 1. What is energy? Total energy for this harmonic oscillator? Can anyone tell me? This is nx is equal to 0 plus half h cross omega plus, this is the first harmonic oscillator in the x direction. Second one is in the first excited state, that therefore 1 plus half h cross omega. The total one is 3, it's 3 by 2. This is 1 by 2. 3 by 2 plus 1 by 2 is 2 h cross omega. This has energy 2 h cross omega. So the wave function is psi 0, 1, which has something like y times e power minus ax square e power minus by square. So because y is in the excited state, something like this. So if we have a particle in the state 1, 0, that means x oscillator in the excited state, y oscillator in the ground state. Total energy is, again, you can figure out 1 plus half, etc. plus 0 plus half. This time it's the second one, which is in the ground state. It has 2 h cross omega. And its eigenfunctions are x e power minus ax square e power minus by square. 1 second, let me. You can clearly see these particles, which is in 0, 1 or 1, 0, have different wave functions. Wave functions are different, but energy is same. Same energy, but different wave functions. Right? Actually, if energy side, there is one energy. Value is 2 h cross omega. This is the value. It's one energy. One value for energy. But the wave functions, there are two different wave functions. So this side, there are two different wave functions. It's like one energy mapped to two different wave functions. This kind of situation, we describe it using the word called degeneracy. We say that the system is degenerate. For the same energy corresponds to two different eigenfunctions. Here, the degeneracy is 2. Sometimes you will be given harmonic oscillator in 2 dimensions, even 3 dimensions. Similar arguments goes through for 3 dimensions also. Then there will be nx, ny, and nz, 3 integers. And then you're asked, okay, given a total energy, what is the degeneracy of this state? You should be able to count. Okay, so that's the point. Let's do one problem and let's look at it. Yeah. So here is the problem. A particle of mass m is in the potential Vxy is equal to half m omega square 4x square plus y square. It's in the eigenstate of energy E is equal to 5 by 2 h cross omega. So they're asking you to write eigenfunction. Sometimes they will give you options A, B, C, D, and pick out the correct eigenfunction. So let us look at it carefully. So please notice first Vxy, it's a 2-dimensional harmonic oscillator. And if you noticed it, if you write it carefully, this is nothing but this is one oscillator, which is in the x direction. Oscillator in the x direction has a frequency 2 omega plus half m. The second oscillator has a frequency omega. So there is a different frequencies. If you are writing energy for this, E is equal to, you will say nx plus half. First oscillator's frequency is 2 omega. Therefore, you write it 2 omega plus second oscillator is regular harmonic oscillator ny half h cross omega. Here nx and ny, they have values starting 0, 1, 2, 3, and so on. And what else is given here? Total energy of this system is 5 by 2 h cross omega. So how can energy be 5 by 2? For what values of nx and ny, energy can become 5 by 2? First, let's see carefully. Nx plus ny, and this is 2 times nx plus ny. There is a 1 plus 3 by 2. I can take h cross omega out and write this way. You can check. This is what it is. Now, this whole thing is 5 by 2 according to the problem. So what values we should put in so that it becomes 5 by 2? So you can convince yourself that it's nothing but nx is equal to 0 and y is equal to 1. Then only this becomes 5 by 2. So that's how you figure out the particle in the system is in the state psi 0, 1. So you will look for the x direction one is in the ground state. That means some constant exponential minus some constant bx square. Y direction oscillator is in the excited state. So what you will expect wave function is something like y minus cy square. This kind of a wave function you will expect. You look at your options and you figure out, yeah, this is the one. So this is how you do this problem. And you can also count degeneracy. Here there is no degeneracy, but sometimes with same frequency, you will be given 3-dimensional oscillator and asked to calculate degeneracy. Or the ground 0-point energy. So that's about harmonic oscillator. At this point, I want to look at time independent perturbation. I cannot stress enough to say that how important this topic is. So you always find time independent perturbation in almost every area of physics. Most of the physics problem, you cannot solve them completely. You have to use approximations. In the approximation techniques, there are 3-4 techniques that you study, but this one is the most important. So let me describe first. You have a system which is completely known. Description for the system is completely known. It has a Hamiltonian at 0. and it has some wave functions you can solve and eigenvalues you can solve. And then you subject this system to a perturbation we usually call H1 maybe or H prime. So this is a perturbation. Subject your system to a perturbation. Then ask, how does energy change due to the perturbation? So the typical answer is without a perturbation, I know the energy is given by En. After adding the perturbation, there will be a correction. And most of you know that correction is nothing but it is a expectation value of H1. This, the new part you have to do. So there can be a lot of problems based on this. Let's look at a couple of them. And we have one here. This is the problem based on the perturbation. So a constant perturbation acts on a particle of mass m confined in infinite potential well between 0 to L. That's visible. So there is an infinite square well between 0 to L. If you have infinite square well between 0 to L, then we know everything. What do we know? We know that psi n is given by 2 over a sine n pi x over a. This is what wave functions are. Energy is given by n square, h square, n square, pi square, h square over k square, 2m width square, a square. Here I use L, so but I'm changing it to N. This is something you do. Now question is, now I change the potential. Potential is shifted. Please note it. 0 to L by 2, potential is shifted to V0 over 2. From L by 2 to L, the potential is shifted to V0. So for subjecting this to a constant perturbation. Your perturbation is, let me write perturbation. What is your perturbation? Perturbation is what happened is it became, or Hamiltonian gets added a V0 by 2 for 0 to L by 2 region, and it became V0. A constant is added for L by 2 to L. When you subject your system to this kind of constant perturbation, how does ground state energy change? That's the question. So we know how to do this. So ground state energy gets additional correction. There is already E0 or E1. Starting is E1. Starting is E1. So E1. And it gets a correction. Correction is you just write 1 and this perturbation and psi 1. This is what it is. Let me do it a little bit elaborately. I'll take a new slide. Correction E1 plus. So we have to go from 0 to L by 2. Between 0 to L by 2, I'll say psi 0 star V0 over 2 and psi 0 dx plus between L by 2 to L psi 0 star. Here the potential is correction. The perturbation is V0 psi 0 and dx. That's it. You finish this and get whatever you can. And that's the answer. Can anyone quickly do what happens to this? So V0 over 2, I'll take it out. And here also there is a V0 out because it's constant. I just have to integrate between this and this. How do I integrate? Can anyone do it? What is the value? Psi 0, that becomes 2 over L. There is a 2 over L. Here also there is a 2 over L because of normalizations. And psi 0 gives you sine square. You have to integral sine square. You need integral sine square. What is integral sine square? Sine square pi x over a. How do you write sine square pi x over a? I think it's integral 1 minus cos 2 pi x over L. You write it this way, and then you integrate it. So if you integrate it between 0 to L by 2, etc. So let me just write. This becomes x cos 2 pi x over L. What is cos 2 pi x over L? Cos is integration. What is cos integration? Cos integration is integration of cos is what? Sine or cos?
Sine.
Plus or minus?
Plus.
Plus. Plus, thank you. And then there is also L over 2 pi. And then there is a
into 1 by 2, sir.
1 by 2. Sine 2 pi x over L. This go from 0 to L over 2. Similarly here, x plus L over 2 pi sine 2 pi x over L, but this goes from L by 2 to L. You can check E1 plus V0 over 2, 2 over L out, and L by 2 becomes 0, 0, sine goes to 0 nicely, and here this will be left over as L by 2. This side V0, 2 by L. Here also sine goes to 0 on both ends, yes. And nicely only x you have to bother. L minus L by 2 is L by 2. So this is what it is. That's it. So you figure that this is.
Sir,
Sorry?
in formula it will be changed. 2 sines ka theta equal to 1 minus cos 2 theta.
No, there is a half. There is a half factor, right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Very good. So E1, and then this is L goes away, 2 goes away, 2 V0 over 4 plus LL goes away, 20 V0 over 4. I think this is correct. You please check. This is how it can be done. Is this correct? Yeah, I think it's correct.
Yes, sir, it is correct.
It's correct. 2 goes away, L goes away, V0 over 2. This is V0 over 4. Here,
Right,
oh, this is V0 over 2. This is 2. Then E1 plus this is 3V0 over 4. This is correct. Now it's correct. So this is the simplest thing you can get, but people won't leave you at that. You can also make it complicated. Let's look at one more. See, second one is intriguing in the sense that, so second problem, it's also based on the perturbation. Let me write the problem. There is a Coulomb potential. Coulomb potential. So VR is minus E square or R. So I am not writing 1 over 4 pi epsilon naught, but everything goes. So you can also think of this is given in CGS units. In CGS units, there will not be any 1/4 pi epsilon naught. So this is of a hydrogen atom. You have a hydrogen atom, and the electron is in this potential, and it is perturbed. This is perturbed by adding a perturbation. B is a constant, Bx square to the Hamiltonian. So if that is so, what is the correction to the ground state energy? So find correction to the ground state energy. What is the wave function in the hydrogen atom? Ground state wave function of hydrogen atom is psi
Square root of 1.
100. You must know. So this is one of those things you need to
A
remember.
cube.
Pi A0 cube. A0 is core radius. This is exponential minus R A0. So this is the ground state wave function. And you can see, because hydrogen atom is spherically symmetric, everything is in the radial coordinates. And your perturbation is in the x square. It's given as x square. So let's write this as bx square b r square sine square theta cos square phi. So conceptually, if you want to find correction to the ground state energy, that is minus 13.6 electron volts. If you want to find correction to that, I am writing delta E, which is that correction, whatever that I think of. What you do is you integrate, and you write here your wave function on 0, 0, and you put in here your perturbation. Let the perturbation act on 1, 0, 0, and then this integral is performed over the spherical surface, right? That is r square sine theta d theta d phi. If you notice, this is when I do this, let me separate pi A0 cube. This is a constant out, and integral, there is a r square e power minus 2r A0 dr. This is the radial part. This is one thing. And sorry?
To the power 4.
Sorry?
Sir,
Hello?
H prime r square, another r square, r to the power 4 now.
Why? Sorry, this is what is the volume element? What is the volume element? Sorry.
R square sin theta d theta d phi dr.
Okay.
Sir, H prime, inside H prime, another r square is there now. That's why it was.
Let me see. This is r power 4. Sorry. There is no dr here. There is also dr. You have to have dr also. R square sine theta d phi dr. So let me write it. So this is r square. Then there is one r square. Then I'll say r power 4. So if you are doing in the entire space, this has to be the case. Next one is 0 to pi. How many signs are there? Sine cube theta d theta, and 0 to 2 pi cos square phi d phi. See, unless you do 1, 2, 3, 4 integrals, you won't be able to finish the calculation. And this one is easy. This one you have to write in terms of sine 3x formula, sine x and sine 3x. Do you know how to do this one, this kind of integral? Does anyone know how to do this kind of integral?
Gamma function.
Something like gamma function, right? Now, suppose someone gives you 0 to infinity exponential minus ax dx. What is the answer? What is the answer?
minus a into e power minus ax.
Minus
E power minus ax by minus a.
So what is the answer? Finally, it's 1 over a, right?
1 by 8.
It's correct, right? 1 over a. It's easy to do. Suppose someone gives you 0 to infinity e power minus ax dx and x. You can write this as minus d over dA 0 to infinity e power minus ax dx. Can you see this? If you differentiate this function with respect to a, you get this function up to a sign minus. So what you can do is minus d over dA, but this function answer is 1 over a. You can differentiate this 1 over a, that is 1 over a square. So this integral is this. You can repeat this process. Suppose you have 0 to infinity x square e power minus ax dx. And this is nothing but you have to do twice. You convince yourself this is so. Please try it and see. And then if you differentiate twice, d square over d square, you differentiate twice. I think answer is 1 over a. If you do it, what is the answer? 2 over a cube. Yeah, I think so. One time you get a square, other time you get a cube. There is a 2, you fix the sign. You can use these things. You can actually make it what is x power n. And on the spot, you can figure out what this is. So you please try these things. I hope they will not make it this complicated, but this is given once. And that is about the first integral. What about the cos square phi? Cos square phi is easy. You go to cos 2 phi and do it. So at the end of the day, I want to tell you, even this complicated integrals you are expected to do these kind of integrals. So please go through some of the formulae in integrations, cos, sine, and these Gaussian functions, etc. You have to keep some sort of take a paper and write these things, and they have to be on your fingertips because you have to be a little faster. So that's what I was trying to tell you. Let's move on. Okay, let's go to the next topic. Next topic I was thinking of is angular momentum. Angular momentum, L. How do we write angular momentum? This is L. This is an operator. Usually angular momentum operator has 3 components: X component, Y component, and Z component. There can be a lot of questions on commutations. What is the commutation between X and Y? Simplify that, simplify this. So please work out angular momentum algebra and especially calculating commutators. So we won't be looking at any commutators today. Instead, how do you describe states, eigenstates of angular momentum? Description of eigenstates of angular momentum. If you want to describe eigenstates of angular momentum, your operators are L square and Lz. You label your states using eigenvalues of L square, which are L into L plus 1 times h cross square, eigenvalues of Lz, which is z component of L, which m, and then h cross. A typical state, if you want to say a state, what you do, you will give L value and m value. That is how you describe this. So needless to say, L square acting on Lm gives you L times L plus 1 h cross square Lm, and Lz have its own meaning, Lm. So don't forget to write h cross Lm. And there are also these operators which often come. L plus is actually defined as Lx plus minus I Ly. So these are rising and lowering operators. Let me write, if we have L plus and it's acting on Lm, and it gives you h cross, and there is some square root factor, L plus 1 minus m plus 1, and it will go to the next one in m. It rises. There is also a lowering. We have Lm state and h cross, appropriately L plus 1 minus m minus 1, L, it lowers. And if you have a state, I'm sure you all know, LL, it cannot rise anymore. It's the maximum value. M takes values from minus L to L. So these things you know. And this is what happens. If you have L minus, and if you have something like, let's say this, then this is also 0. So based on this, sometimes it's important to remember. Similarly, you can have spin. Spin what? Spin is given by, how do you describe spin? Spin is described by this operator. It also has these components, Sx, Sy, and Sz, and these are described by operator S square and the z component of S. The eigenvalues of S square are S plus 1, h cross square. Eigenvalue of Sz is, there is another z component. Usually we write ms to distinguish it from the L. So a typical state, a spin state, is described by, for example, I'll give you S is equal to half. If you want to describe S is equal to half, we'll say S is equal to half, give me ms value. It can be plus half, or S is equal to half, ms value can be minus half. So states are given by S and ms. This is how you write. Similar story, it also has a lowering and highering operators. General spin state could be different, but these things are used as a basis. Let's start with a simple problem in spin. Please read the problem. Does anyone know how to do this problem? So it says the basis is set. In the beginning, it said in a basis in which z component of Sz is diagonal. Operator Sz is diagonal. In which basis operator Sz is diagonal? If you have this kind of a ket, if you write it as 1, 0, if you have this kind of a ket, if you write it as 0, 1, then you can write Sz, a matrix representation. Sz matrix representation is 1, 0, 0, minus 1 multiplied with h cross over 2. So he's talking about this basis. You should know in the beginning itself. In a basis in which z component Sz of the spin is diagonal. That means he's talking about this kind of a setup. If you have this, there is a spin state S psi, which is 1 plus I or root 6 and root of 2 over 3. This state is given. You need to find the probability that the measurement of Sz will yield plus h over 2 or minus h. What is measurement of Sz over 2? The meaning of measurement of Sz over 2. So if you want to find the probability of Sz, suppose you want to, let us say, there is a state psi, take this, and you're measuring Sz. So Sz, and it should give you plus h over 2. That means it's spin over 2 plus half. This is the probability. See, what does it say? If you measure Sz, this tells you the probability of, sorry, there is no Sz, just this. It should give you this value. Psi. There are two states, and half. That tells you plus h by 2. Sz value for this one is plus h by 2. Given this state, the probability that you find plus half is this. This probability that you get plus h over 2. Similarly, if you have this, this is probability that you get minus h over 2. This is the interpretation. So any general state has to be expanded in eigenstates of these. So we have here eigenstates. Let us do it. General state psi can be written in terms of 1, 0 plus something 0, 1. You can do that. If you do that expansion, you can figure out inner product. This expansion tells you first one is 1 plus I over root 6. Second one is root of 2 over 3. Root of 2 over 3. Now, if you are interested in computing, let us say this. This is nothing but you put this vector psi star. You put a column vector, row vector. Write a row vector of this, and then how to write a row vector of these? Take a complex conjugate 1 minus I over root 6. 1, 0, it's a row vector, plus root of 2 over 3, 0, 1, a row vector. This is one thing. And then there is a matrix thing. On the other side, you have 1, 0. Take this inner product. This is the meaning of this. The bras are written as row vectors. Kets are written as column vectors. Half correspond to 1, 0. So you get, what do you get? Only the first one gives you something, that is 1 minus I over root 6. Second one is 0. But what we need is this. The probability is mod square. So that tells you 1 and 1 over 6. 1 plus 1 over 6. I think it's 1 plus 1 over 6. What is 1 plus 1 over 3? Sorry, this is the whole 1, 1, 2, 2 over 6 is 1 over 3. This is the probability 1 over 3. Similarly, you can compute half minus half, where that comes out to be 2/3. Okay. How many of you are able to follow this? Let's see. Okay, Mosam knows. Anyone else? One, two, three. Not many. See, this is an important thing. Okay. Not many of you are able to follow this. This is the crux of quantum mechanics. Given a state, how do you find measurement probabilities? They give you a state and they tell you we are measuring this. What is the probability that you get this value or this value? So this kind of a thing is very, very important. This is the, if you understand this, you understand actually the quantum mechanics. The whole quantum mechanics is in this expression. Okay. Anything. Suppose I give you a state psi. Okay. And I'm measuring. This is the state psi. I am measuring. What am I measuring? I need to set an observable A. I'm measuring an observable A. And then eigen functions of A are given. For example, phi1, phi2. The eigenvalues of A is given. For example, lambda 1, lambda 2. So I tell you there is an observable A. It has eigenfunctions phi1 and phi2, and it has eigenvalues lambda 1 and lambda 2. I'm measuring this observable on this state. What is the probability that I find lambda 1? What is the probability that we find lambda 1 as value when we measure A? This is a question, very specific question. That is given by psi lambda 1's eigenfunction. What is lambda 1's eigenfunction? Phi1. And you square it. This is the one. You can also do it more abstractly. You can expand psi in terms of phi1 and do the coefficients also. But you always have to remember This is the thing. If you want lambda 2, what is the probability that we find lambda 2? Then you do the other one. So same thing I'm doing. Let me do the same thing. Let us see why do you, let me convince you. So in the case of our thing, psi is given, something is given. And then there is an observable SZ. This observable has states, eigenstates, plus half. This was 1. Minus half. This is 1 more. It has eigenvalues, plus h over 2, minus h over 2. Now I ask, what is the probability that we get value plus h over 2 when we measure SZ? Answer is, take this psi, half and plus half. You have to sandwich psi with eigenfunction of your measurement. The value is h over 2. The eigenfunction is this. You sandwich and you take square. This we do it very often, and try to get this kind of picture in mind. Okay. Let's go to the next
Hello.
one. Yes.
The previous question. It's a question.
This
Sir,
one?
yes, sir. Sir, this is in the size Z basis, so it's easy to calculate SZ. But if they provide in size Z and say that calculate in X direction, like psi X, SX, then
No.
how we can?
What is given?
This is given in SZ basis, no? So it's
Yes.
we
Yes.
can write, we can directly write that
Yeah.
psi in that basis. But they, if they provide in size Z basis, but ask in X direction that what will be probability plus h squared by 2 minus
No,
h
I
squared by 2.
didn't understand. If you're given SZ basis,
Yeah, then they did not ask in that SZ. They will ask in that SX or SY.
probabilities are basis independent. Okay.
Okay.
But I understand what you're trying to ask. Sometimes they can ask you other things like SX, SY, SZ.
Yes, sir.
You mean if the basis is changed, what to do?
Yes, sir. Yes, sir.
See, you know, right? 1001 are eigenvalues, eigenfunctions for this matrix.
Yes, sir.
So if you are looking at Sx and Sy, what are the eigenfunctions for Sx and Sy? That you have to see. And I hope you all know S matrices. Let me write S matrices. S matrices. Sx is, the matrix is H cross over 2. What is Sx? 0, 1, minus 1, 1.
Yes, sir.
Sy?
0. Sir, 0.
I, Z. These are Pauli
Will
matrices.
be 0, no? So,
Hmm?
sir, SX last element will be 0. Trace will be 0, no? So, last element will be 0.
Like this. No, what are you saying? This is the
Sir,
matrices.
SX
Sx is
last element will be 0.
yeah.
Yeah. Yes.
So if you know these matrices, you can find corresponding eigenvalues and eigenfunctions. But if you want to change it to other basis, you have to perform a basis change. But that can be done. Whatever it is.
Yes.
Okay, by the way, if you have questions, I mean more questions, so you can write to me. Here the conference, after this workshop also. Subject, you put in some, this and whatever. What is this? National workshop something 2023 or something. You write a question within 2-3 days or some time. I will give an explanatory note and provide you answer. Okay, that I can do. So after this workshop also, if you have any questions in quantum mechanics, please write to me. So Mosam, you do that. I don't quite understand what your answers. Okay, let's move. If so and so thing is given here, if psi n l m denotes eigenfunctions of the Hamiltonian with the potential V is equal to this, then find expectation value of this in the state psi. This is very easy, but you have to do it. How do you do it?
L square.
So
L square
there's a neat trick. There's a trick here. Whenever you have x square plus a y square, you can write lx square plus ly square plus lz square. You know that this is equal to L square. And because of that, x square ly square is equal to L square minus lz square. You can do that. And once you have it, you can figure out what this value is. First, let us figure out what is L square expectation value. You can look at now at this point, you should be able to look at it and write. L square is easy. There is a 2 times psi. So there is a 1/25. And there are orthonormal states. So 3 and 3 is multiplied. There is a 9 here. And then because of L square, there is a h cross square here. L into L plus 1 gives you, for the first one, 1 into 1 plus 1. That is 2. That is the first one. The second one is again 2h square. Third one gives you plus and 15. Again 2h cross square. This is it. So that says you 2h cross out. 9 and 1, 10, 25. 25, 25 will go away. 25, 25, and 2h cross square. So this is the answer. Lz square. That's also you can figure out. It's easy. Let me do Lz square again. 1/25. 3 3s are 9. You have to square 1. So this is square plus here it's 0 plus 15 h cross square. H cross square because it's Lz square. Lz value is -1. That is 1. So that's it. So 15 and 9 is 24. This is 24/25 h cross square. So appropriately you take the difference and that's your answer. Okay, so that's how you do this problem. Any questions on this?
Sorry, LZ last term -1. Yeah. For LZ,
Lz?
the last term is m is -1.
This one is -1?
Yes, sir.
mz square, sir. So plus.
So you're right about Lz. If you have 2, 1, -1, what you get is -1 times h cross, same thing. But when you have Lz square, you have to do it twice. So -1 times -1 is 1. So that's how there is no minus. You understand?
Okay, sir.
Similarly, there is no, this minus also goes. Why? You understand, right? You have to do twice. Does anyone want me to do this once more? I don't know. Someone is speaking. I have no idea what's happening. Okay. One more of that sort. Here you have expectation value of Lx. You have a very long expression and they're asking you to find Lx. Now this is difficult. How do you find expectation value of Lx? If you want to find expectation value of anything, you need to know how that operator acts on these functions, wave functions. For example, I know how L square acts on psi NLM. I know this. So I can find expectation value of L square. I can find expectation value of Lz because I know how Lz acts on this. But I don't know how Lx acts on this. What else I know? I also know about L plus. I know how expectation value. This also I know. This also I know. But Lx, I have no idea. So what you can do is you write Lx as rising and lowering operators plus L minus over 2. You go back and check the definition. And then you can figure out one by one.
Yes, sir.
So let's start. L plus, let me write some L plus expressions. This is also tedious. There is a lot of algebra you have to do, but it's good to do once. Let's start with L plus acting on psi 211, psi 21 minus 1. The answer is what is the answer? H cross. You remember the formula square root of something something L times L plus 1, that makes it 2
So it's got
minus 1. So what is the value? Minus m times, that is minus 1. Minus 1 plus 1 is 0. So that's it. It's only root 2. There is nothing more. It's very
yes, sir.
simple. Only root 2. So this is the root 2. And then you have psi 2, 1, 0. It rises. Similarly, L plus acting on 2, 1, 0 gives you H cross root 2
Root 2.
psi 2, 1, 1. And L plus acting on psi 2, 1 plus 1 gives you 0.
0.
So we know this much. Then you can figure out expectation value of L plus first. Expectation value of L plus, because we have all this and we have this setup. We can say 1 over 5, 1 over 5, which is 25. There's a 2110 goes with, there is no
Root
2110.
it's got
First one is 0. 210 goes with 210. That is root 5 times 3. Root 5 times 3
no, sir.
and root 2 times
Sir,
H cross. Is that
how-
correct?
Yes, sir.
Two one one zero. There is no 2110. There is a 210. Yeah, this is correct. And I hope you understand what's happening. I'm doing this and this. If you want, let me do it anyways. Since I have one side 1/5 3 psi 2 1 minus 1 plus root 5 psi 210 minus root 11 psi 21 plus 1. I have this on one side. Okay, for example, you have this. On the other side, when I add L plus on the entire thing, again I have 1/5 3 psi 2110 became root 2 h cross psi 210, and 210 became root 5 root 2 h cross psi 211 plus 0. This is what I have. Now you can see now equal to 1515. You see 1/25. You multiply this with which one? No one. No one goes. So this is gone. This one pairs with no one on this side. So you get 0. But this one pairs with what? 210. This. That gives you 1 because they're orthonormal. And then I have 3 root 2 and root 5 is 3 root 10. And then there is also h cross. That's good. And this one goes with this one. That gives you what? Minus root 55. And then h cross. This is the answer. So it's complicated, but this is the answer. Similarly, you have to do it for L minus and add them and do half. Then you will get your answer. See, it's pretty complicated. How much time do you have usually for these problems?
110, 110.
Hmm?
The 55 or 110.
It simplifies to 110. Did you do
Sir,
second?
root
2 is also there, sir. Root 2 is also there, sir.
Yeah, root 2 is also there. That's why it's root 10.
Yes, sir. Root 10 into root 11.
No, yeah, this one is root. There is still, you have to find L minus also. And then figure out, add both of them and do half. So at the end, the answer at the end is pretty complicated in terms of root, because you will be given A, B, C, Ds. You will be quickly come to this. So how much time do you usually get for doing these kind of problems? Five minutes, 10 minutes? In the past, these problems were given. At least you have to know these expressions. These are all as expected. How to do these things. Okay. Any questions on this part? Please do this. Can someone do this? And I'll wait for a minute and tell me what is the answer.
Two minus root 2 is cut.
Hmm?
Two is cut.
2 is cut.
Hmm. Okay, that's good. You have any more questions on spin and angular momentum? Okay. Addition of angular momentum. Here, the angular momentum can be spin or orbital angular momentum. So how do we add? Suppose I tell you that there are two states, and when we add angular momentum, what are the possible outcomes? Let's look at spins. There are two electrons. The first one is S1, operator S1. The spin of the first electron is represented by S1. The spin of the second electron is represented by S2. And obviously, they have their own eigenstates. Okay, so what do I say? For example, if S1 square is acting on the first one, half and plus half. This is the first one. You obviously get half times h cross square, s times s plus 1. S plus 1 is 3 by 2, 3 by 4, 3 by 4, and then you get same state. So that says that spin of the first electron is this much. So sometimes you will get a combined state. A combined state is one which looks like this. Half for the first one. The second one, half and whatever, something minus half or whatever. That's second one. This can be equal to a new state, but not for the spin half, but spin 1. The new state, it can be written as new state. So what are these new states? They are given by the rules of addition of angular momentum. If I add spin half and spin half, what is the answer? What are the possible values I get in addition of angular momentum? Suppose someone tells you that there is a eigenvalues for spins are S1 plus S2. If you add two spins, possible values are S1 plus S2, S1 plus S2 minus 1. In steps of 1, you go up to S1 minus S2 modulus. Have you seen this kind of expression?
Yes, sir.
If this is the case, you should know that when I add half and half, possible spin values, if I add half and half, the possible spin values are, you add both of them first, 1. After that, in steps of 1, I have to go. Next one is 0. And that is all, 1 and 0. So if you have two electron wave functions, they can be written as 1 and 0 also. Here the spin is 1, here the spin is 1. So two electrons with spin half can be thought of as different particles with spin 1 and spin 0.
So why minus
Particles, sorry,
why -1 is not there? Because two electron are minus up, so it will be -1. No?
what -1? These,
Sir, first are plus up, second are plus up, it become +1. So first become minus up, second
okay,
become
listen,
minus up.
listen. This is S1. This is S2. These are possible values of S. Okay. But I am not saying anything about M1. I'm not saying anything about M1, M2, or M corresponding to this. I am not talking about Z components of these spins. This addition refers to the actual spins, not the Z component. How Z components are added is another question. This addition is for addition of spins. The eigenvalues, S1 is eigenvalue of S square. If it states act on it, this one is S1 times S1 plus 1 H square, this one. I'm talking about these. So there is another way you also can talk about Z components, but that's not what I'm talking. So you always remember, in addition of angular momentum, what you are adding are spins, not the Z components. So I'll stop here. Maybe I'll start this subject again tomorrow sometime while doing atomic physics. If you have any questions, please write to me, or you can ask me now itself if you have some questions. Okay. Tomorrow, in the next session, I'll talk about addition of angular momentum, hydrogen atom, if possible. So far, we discussed quantum mechanics of one particle, single particle, one particle states. Probably, if there is time, I will tell you something about two particle states. How do you keep two particles in a state and its implications to Pauli exclusion principle, etc.